Hello, I'm Dr. Carlos Gaitan, research scientist at the South Central Climate Science Center of the University of Oklahoma. I work in Princeton, New Jersey at the Geophysical Fluid Dynamics Laboratory of the National Atmospheric and Oceanic Administration. In this video, I will introduce the concept of downscaling and discuss its advantages and limitations. By now, you are familiar with global climate models, or GCMs. These numerical representations of the global climate system generate thousands of variables like temperature, pressure, and winds at every single step at many different layers of the atmosphere, ocean, and land. However, because of their very high computational cost, the climate modeling centers around the world have had to compromise the spatial resolution of their models so they can produce longer time series. These time series typically include daily climate data for about 200 years and are needed to analyze the long-term effects of atmospheric greenhouse gases in the climate system. As a result, the current generation of GCMs produces results at the spatial scales that are too coarse for many decision makers and climate impact researchers. Finer scale climate information is usually obtained in three different ways. First, by running a higher resolution GCM. Second, by implementing a high-resolution nested climate model using the boundary conditions provided by the surrounding GCM. And third, by using statistical downscaling methods. The first approach involves running the already computationally intensive GCMs at higher spatial resolution. Unfortunately, doubling the spatial resolution of a GCM generally requires 16 times the volume of computations to be made. Thus, it is unlikely that anyone without access to immense supercomputer resources will use this approach. The second approach generates finer scale information using regional climate models. This approach is known as Dynamical Downscaling, and it is less computationally intensive than the first one because it only models a small part of the globe, such as North America. Nonetheless, it still has a high computational requirements that can make it impractical to practitioners with access to single workstations. On the other hand, the third technique, known as statistical downscaling, is based on finding statistical relationships between the climate variables from the coarse resolution GCM outputs and the finer scale observations. The statistical technique is less computationally demanding than the other methods and can be completed using desktop computers. Overall, the statistical and dynamical downscaling techniques have advantages and limitations. Both aim to solve the scale mismatch problem and provide future projections for decision makers. However, we need to acknowledge that both rely on stationary relationships. In the case of statistical downscaling methods, we must assume that the statistical relationships between the climate variables from the coarse resolution model and the observations remain unchanged in time. When using downscaled output, you must understand the underlying limitations and characteristics of the numerical model used to create it. For example, was the model designed for short-term weather forecasting, or was it a regional climate model? If you are not aware of the data origins, you could compare observations from the first decade of this century with the corresponding values from different downscale climate projections, only to find out that the data are not correlated. Some regional model developers might be tempted to run a weather model for a longer time, hoping to produce climate projections. However, as you remember from the video about GCMs, there is a substantial difference between the initial value problem of the weather forecast models and the boundary value problem of the global climate models. Also, it is important to understand the method used to produce the downscale projections. If you used statistically downscaled projections, as many decision makers do, you need to know that not all the methods are created equal. Some methods are designed to produce more accurate mean states of climate variables, such as an average monthly precipitation amount. Other methods are designed to compromise the mean state performance in order to improve their behavior, simulating extreme events, such as maximum daily precipitation amount. Similarly, some statistical downscaling methods are designed to improve the representation of a sequence of events like heat spells or consecutive number of wet days. And some methods focus on improving temporal correlations, while others are more appropriate to analyze spatial behavior. It is also important to recognize that often decisions are made using only one source of information, that is, one GCM downscaled using one technique. This approach neglects the uncertainties associated with the global climate model projections or with the type of downscaling method used. As a result, decision makers who use only one source of information will likely have a false sense of confidence in their decisions. Overall, I recommend that potential users of downscaled data not use the available datasets blindly. You should first investigate the assumptions and limitations of the method used to produce the data product. You can talk with experts at your local climate science center, state climate office, or similar organizations to help guide you. When you understand the products well, you can apply downscaled climate projections to many important planning needs.